My name is Vijay Chobisa. I'm from Siemens Hardware Assisted Verification Division. And today we're going to talk about enabling new era of software shift left with Veloce CS. But before we talk about software shift left, I would like to talk about few trends which we are seeing in the industry. So first one is, there's a lot going on about the software. Software is defining what hardware gonna looks like. The customers are doing purpose-built accelerators or custom SoCs to drive what the hardware should be doing. Right? They are not counting on general purpose ASIC, and they are doing these the purpose-built accelerator to make sure they are able to execute those workloads efficiently, also in the very cost-effective way, and able to deliver that power and performance required for executing those workloads. So that is the trend, number one trend we are seeing. The second trend we are seeing is the focus has shifted to system level, to design, validate, and optimize. And for that, you need a system level simulator, people call digital twin or digital representation. So you need a system level simulator so that you can design, optimize, and simulate the entire system together before you build the real system. I think the third one is ARM architecture native acceleration. So this is an inflection point in our industry, and Siemens understands this trend very well, and we're going to talk about this in this presentation. And finally, chips and systems are getting very complex. And in order to verify those chips and systems, you need a complete hardware-assisted verification engine that provides you the scalability, that is able to handle that complexity, but also deliver that performance where you can execute those software workloads and software applications. So with that, let's start. So semiconductors are driving innovation in all the applications. So it is from aerospace defense, it could be consumer devices, the medical, factory automation. It is driving advancement in all the industries. And if you can look at the advancement, like the remote surgeries are happening in medical science. Doctor don't need to be the close to the patient. Machines are doing operations. The self-driving cars, the robo-taxis, smart cities, factory automation. So the semiconductors are impacting all the applications. And if you look at the software-defined, silicon-enabled, and digital transformation, and also AI, these are the critical the aspect which are driving these advancements. So the quote from the Amazon here, James Hamilton, he's talking about what rate things are evolving. So if you look at, they are bringing 6x more capacity every day versus what they had in 2006. So this is the rate where things are evolving. So we are in the era of system. That means, the focus has shifted to the system, right? We are designing, optimizing, and verifying at system level. An old way of doing the systems are not adequate for the today's complex system. Electronics and semiconductors are impacting every aspect of the system. And system is not only just electronics, system is hardware, system is software. So system has the mechanical part. If you are designing car, you have actuator, you have sensors, you have battery. So it is very important that in very early on, you have system level view where you are able to put the system level component from various domains and build that system, and you are able to simulate that system to make sure that you are designing, you are optimizing all system level component together. And not to say that AI is a very critical part of every system. So let's look at what is industry is saying about the purpose-built accelerators. NVIDIA, NVIDIA and Intel, they are doing the purpose-built accelerator for driving, the deep learning. AWS is doing for generating AI. Tesla doing the purpose-built accelerator or custom chips for self-driving car, or now even they are talking about the robo-taxis. So these companies are doing the purpose-built accelerators. Also, if you look a quote from Anand Joshi from semi-engineering, he's saying that AI ASICs will become more application specific. So you are designing a hardware that is targeted for the application you would like to run, nothing less, nothing more, because you need to make sure that you are able to deliver a system in very cost-effective way, but also on schedule with the power and performance required to execute those workloads. So let's look at what hyperscalers are doing. The hyperscalers are already doing the purpose-built accelerator because they would like to execute a very specific workload targeted for that application. They are not relying on general purpose ASICs or general SoCs coming from the companies. So here, Microsoft is Maya 100. If you look at Google, is TPU, Axion. From Amazon, Graviton, Graviton 2, Graviton 3. And Meta is doing the inference accelerator. So there are a couple things which are common, which I would like to highlight here is, one is these hyperscalers are doing their own purpose-built accelerator to target to run those workload in very, very efficient way. So that is the one trend. The second trend I would like to highlight here is they are all ARM architecture. They are using ARM architecture, and they are using ARM compute subsystem that is targeted for their specific application. So I mentioned earlier, lot is going on the software. So software defines the product success. Software is dominating the design cost. Software is a differentiator. You need to have a software ready before you sell your silicon, you sell your system. So software is getting item to your revenue. If you are not ready with the software, you won't be able to ship the system. On the right-hand side, you see this graph from the IBS. And what this graph is showing here is, as we are moving to the smaller node geometry, the software and verification are the biggest cost and biggest effort. On the hardware side, also you see the graph, as I mentioned earlier, chips are getting complex, chips are getting larger, and the customers are doing 2.5 3D heterogeneous integration to keep up with those challenges. So transistor counts are increasing, but the important thing is, as I mentioned earlier, there's an increase in the workload optimized chip. More and more customers are doing the chips to make sure they are not using general purpose ASICs, but they are designing the hardware that is helping them to optimally run those workloads. And also doing that because of, because of the cost, and also delivering the performance in the given power budget. So it is important that you start very early on, where you have a platform where you're designing and developing software and hardware together, and also that you are optimizing the software and hardware together. So as I mentioned, lot is going on the software, software defining what kind of hardware you're gonna build. Also system level focus for design and verification. These trends and these requirements, what kind of challenges they are bringing to industry. So first thing is software defines everything. Software is differentiator. That means the hardware is designed and optimized for executing that particular software workload. In the previous days, you build the system and you ask the software guys to write the software. Those days are gone. Now software guys are telling the hardware team, this is the exact hardware architecture I need in order to execute my software workload. The software workloads are becoming more complex, long, and also diverse depending upon what application you are targeting. Also, we saw on the previous slide, the complexity of chips and complexity of system is increasing. That means you need to validate all this functionality, but not only functionality, the power performance is very important. If you are not able to deliver the given performance in the power budget, you will miss the market opportunity. Also, for some industries, the functional safety is very important, like for automotive. Let's not forget security is very important. So there are a lot more other aspects to verify for a system in addition to the functionality. And finally, the software shift left, providing a platform for the software guys very early on so they can do the architectural exploration. They can do the what-if analysis on what architecture is best suited for the given application they are targeting. So doing the shift left where you start everything early on, this is very important. So what are implications? What other things we are seeing in the industry? One is the cloud-ready solution, cloud-ready access, depending upon how much you need, when do you need, what you need. So cloud is a big thing. Customers are looking for solutions which are ready in the cloud, but also they are secure. The solutions are scalable. Also, you need a platform that can handle the software and hardware complexity. As I mentioned, systems are getting very complex, and you need the verification and validation platforms that can handle that complexity. And it is for both software and hardware. And finally, for designing a system, the tools are not enough actually. You need the entire ecosystem. Take an example, if you are designing system, you need interfaces, you need hardware, you need model for the mechanical part. So you need an entire ecosystem where you can say, I'm gonna put a system together, I'll run the simulation, and I see, what kind of architecture is right for my hardware, what kind of the architecture is right for my system component, what type of battery I need or what kind of, engine I need. So system level simulations are very important, and you need models for that. You need mechanical model, you need model for sensor, you need model for actuator. So entire ecosystem is very important. So let's look at what are the components for effective software strategy, right? You need, as I mentioned, you need both hardware and software platform. So first of all, the virtual platform that allow you to put the entire system together with the virtual models. Virtual model can be, TLM model, System C model, ARM fast model. With this model, you can do the what-if analysis, say what kind of architecture I'm going after, which is the right architecture for a particular application. The second one is tooling. You need the right tool for software guys where they can do the software development, they can do hardware software co-design, they do the visualization, they do the analysis. And the other one is system level simulations. This is very important, people call digital twin, digital representation, system level simulation. My view, pretty much everything is same. Here, this allows you to put the entire system together, irrespective of what kind of component you have. You have hardware, you have software, you have sensor, you have actuator, you have mechatronics. Models of the entire system you are able to put together, run those simulations, see how those system components play with each other. What are the impact of each component? So you are able to design, co-develop, and optimize together. And finally, for these complex chips and system, you need a complete hardware-assisted verification platform, which you can give to your software guys, and they can do development, they can do the optimization, they can do the co-design of hardware and software together. So this slide is very, very important actually. And this gives you the view of how the methodology and tooling looks like in order to achieve that. So on the left-hand side, you start very early on with a high-level model, we call virtual model. So you have the virtual model of your SoC, and on that model, you are able to run the software, the application, and now you can do as I mentioned, you can do the what-if analysis of your architecture, but also you can draw the KPIs for your design, how my power looks like, how my power performance looks like, what are my functional safety goals. So you can decide the KPIs very early on with the virtual model. And as you are making the progress in your chip and system life cycle, At some point, you can say, I have a hybrid model where some components are ready. These are actual models. Those are RTL models. But some components are still the high level. And finally, at some point, you're going to have a complete, accurate representation of your system. So beauty of this particular methodology and flow is you are able to run exactly same software workload, same software application, irrespective of you are in virtual environment, you are in hybrid environment, or you are in a fully accurate environment. And in the event of the gap, you see that you are diverging from your KPIs, you can go back and see where is disconnect. You can go back to hybrid model, you can go to fully virtual model and say, what is going on? So let's talk about the software. As I mentioned, both the platforms are important. The platform for software and platform for hardware. Both the platforms are important. So let's start with the software. Virtual prototyping and virtual offering is just not tool. It's an entire ecosystem, right? And Siemens, ARM, and AWS work together to provide that. PAVE 360 from Siemens, it is targeted for automotive. ARM provided the compute subsystem that is targeted for automotive, and AWS enabled that in cloud. So now, because of this relationship, you have a complete virtual acceleration environment for your software-defined vehicle, SDV, in the cloud. You can run those simulations on the cloud and see how all the aspects of the cars are playing together. How your compute subsystem is playing, how your actuators, your steering wheel, those models are interacting, how your sensors are sending the data to the system. So you can build the entire the car in the cloud and run those simulations and see how things are impacting each other. So this is a slide just talking about ARM announcement about compute subsystem virtual offering, which is based on the ARM Cortex A720. This is Hunter family. This is where ARM has done the announcement, and on the portal they have said what is simulated, what is verified, what is enabled. Siemens is fully ready with this offering. As I mentioned, using AWS cloud and ARM compute subsystem, which is targeted for automotive, you can run this simulation for software-defined vehicle. And we are the first one to deliver this environment in the cloud. So let's switch the gear and let's talk about the hardware. As I mentioned, you need software, you need the hardware. And as today's chips and systems are getting complex, you need the right platform depending upon which stage of your verification and design stage of your chip and system. So very early on, you need an emulation platform to shift left, where your target to get the hardware right. This is where you need a very fast compile, fast compile turnaround time, and faster bring up. Also, you need full and fast visibility, so you can go and see what is happening in my design when things are not working. So you don't need to reiterate many times to compile. You should be able to see everything what you want to see with the default compiles. And also the system level aspect. As I mentioned, just verifying functionality is not enough, right? Power performance is very critical. If you are not able to deliver performance in the given power budget, you may have non-starter. It will not generate revenue for you. Other use models are becoming important for emulations are functional safety, design for test, and gate level emulation. So with the emulation, you start very early on, shift left. The focus is to get hardware right. So once your environment is reasonably stable, where you are not doing multiple compiles a day, right? You can move to the enterprise prototyping, where you can execute this workload much faster, but also in cost-effective way, because enterprise prototyping provides you the density and acceleration, which gives you a very cost-effective verification. The important aspect is emulation and enterprise prototyping get used together. So the congruence is very important. you should be able to take the entire emulation environment. And when I say entire emulation environment, is not just the chip, your peripheral, your script, the analysis data. You should be able to take everything from emulation to the enterprise prototyping and run that as is. Very, very quick and smooth bring up from emulation to enterprise prototyping. But in the event of the problem, you should be able to go back very quickly to emulation for doing the detailed debug. So this path from emulation to enterprise prototyping and back is very, very important. And finally, software prototyping. It can get used for IP development, SoC development, and system-level software development. So focus is software development and system development. And requirement for software prototyping is performance, and you can say 100 type performance because software guys want performance, the flexibility, and at-speed interfaces. At some point, you would like to run the at-speed interfaces to see how my system is behaving. Is my system doing things what it is designed for? So software prototyping, performance, flexibility, and at-speed interfaces is very, very important. So this is the deck. I'm not going to do a product pitch, but let me give you a quick view of what is Siemens EDA has announced in February this year. So Siemens EDA has a complete solution for hardware-assisted verification. And as I mentioned earlier, we are the only vendor doing the custom accelerator for our emulation. Why? So emulation, we have our crystal chip. This is many generation of chip we are doing. The reason we are doing chip is fast compile time, reliable compile time, full debug visibility, and scalability. And this is our emulation platform looks like. It's called Veloce CS, and it is giving 5x performance over our previous generation. So you can take the workload, which is taking 5 hours today, you can run that workload in 1 hour with our new platform. Enterprise prototyping, this is Veloce Primo CS. And as I mentioned earlier, when you are not compiling a couple times a day, the focus is not compile time, focus is not debug, focus is execution, performance. You move those workload to enterprise prototyping platform, Primo CS, and it is giving another 5x acceleration over the emulation platform. Not only that, it is giving you 3x density so that you can put more systems into the data center and you can run things more cost effectively when you are using the combination of emulation and enterprise prototyping. The software prototyping is our Pro FPGA CS system. And as I mentioned, the goal of this product is performance, flexibility, and at-speed targets. And this is giving you another 2x performance over our previous generation platform. The one couple point I want to highlight here is you can see that emulation platform is built with the Veloce Crystal Lake chip. This is our custom chip. Siemens is designing that. But enterprise prototyping and software prototyping, they are based on VP1902 chip from AMD. This is the latest chip. And I'm glad to say here that we are the only vendor shipping the prototyping platform to our customer for production use as of today. Okay, and systems are scalable. As I mentioned, scalability is very important. You can start using from IP to SoC to system. So we can scale from 40 million gate all the way to 48 billion gate. So system can be as big as you want. We have the scalability, we have the platform that can handle that complexity for all these platforms. So how the system looks like? We have changed our architecture. We have moved to the blade technology, right? We don't need those bulky chassis where you put a chassis and put the board into that. We just got rid of that. You buy as many blades you need. You need one blade, perfect. You buy one blade, you connect the host, you connect the power, you have emulator. You need 10 blades, you buy the 10 blade, you connect those, and you have 10 blade emulator. So you don't need to worry about those bulky chassis moving through the accelerators, elevators. Those days are gone. The other thing is our systems are fully data center compliant. Nobody's keeping hardware on premises. Everything goes into colos or data center, whatever you want to call. Our systems are fully data center compliant, air cooled, hot aisle, cold aisle, air cooling configuration, you don't need water. Some of the platform needs water, you know that very well. And you ask the data center guy that I need to bring a water pipe in the data center, you will get a big pushback. So our systems are fully data center compliant. No water is needed. To summarize, we have 3 leading edge platforms because you need the right platform depending upon what task you are trying to do. The second thing is this platform is scalable, 40 million gate to 48 billion gate. And because of our purpose-built accelerator, we are able to provide the compile, the scalability, visibility, and congruency with our enterprise prototyping platform. So to summarize, the couple point actually. So we are in the new era of the systems. Verifying the pieces is not enough actually. You need to have a system where you can design, you can optimize, and you can validate entire system together. And software is a big differentiation. Software is defining what kind of hardware is needed, what specification, what KPIs are required to execute those workload. And, these requirements, these trends in the industry has created impact on EDA industry. And as I shared in my presentation, we are responding well. We have adapted to what industry is looking for, and we have changed our roadmap, our offering to adapt to that. And finally, Veloce CS, which is our hardware-assisted verification platform that includes emulation, enterprise prototyping, and software prototyping, is delivering shift left for chip, software, and system-level verification and validation. With that, thank you all.